One of the reasons why Go became so popular is its inherent support for concurrency. The main building block of concurrency in Go are Goroutines, lightweight virtual threads of execution that are dynamically mapped onto real system threads and CPU cores. This video demonstrates an easy way of turning single-threaded code into concurrent code. The key point is to look out for loops in your code. Loops provide an excellent opportunity to add concurrency. The example used here is matrix multiplication. The code is as simple as can be. The matrix type is a slice of vectors, and the vector type is a slice of integers. The matrix multiplication method does some sanity tests, creates a matrix for storing the result, and then enters 3 nested loops to multiply the 2 input matrices. The outer loop iterates over the x dimension of the first input matrix. On every iteration, it creates a new result column, and the 2 inner loops then do the hard work. Let's see if we can make the inner loops run concurrently. First, we turn the inner loops into a function that we call immediately, passing the outer loop index I into it. Now we can easily verify if there are any write conflicts. Does a function call overwrite the results of a previous function call? No, because the function writes into column I of the result matrix, and I is different on each function call. This means we can trivially make the function calls execute concurrently. We only need to add the keyword go before the function call. Now every iteration of the outer loop spawns a new goroutine and does not wait for this goroutine to finish. The goroutines can be distributed to all available CPU cores and run independently of each other. But here is a catch. If the main thread of execution does not wait, then it might return too early, passing back an unfinished result matrix. We definitely need to wait for all goroutines to finish. There are several methods available to accomplish this. In our example, the goroutines do not return anything and do not produce any errors, so we can use the simplest tool to wait for the goroutines, a wait group. Wait groups are defined in the sync package and are used as follows. First, we define a new wait group. Then, every time the code spawns a goroutine, we call add1 to keep track of the number of goroutines. At the end of each goroutine, we call the done method to signal that the goroutine has finished. Now we just need to call the wait method at the point where we need to wait for all goroutines to finish. The wait call blocks until all goroutines have called the done method. Now we can be sure that the returned result matrix is complete. Let's do a quick benchmark to see if the concurrent code runs considerably faster than the single-threaded version. I have prepared a benchmark function that multiplies 2 500 by 500 matrices. This means we will spawn 500 goroutines for this test. However, how many of them are executing in parallel depends on the number of available CPUs. With only one CPU, we cannot get any faster than the single-threaded code. However, let's see the speedup on 2 and on 4 CPUs as well. For this I call goTest with the bench option and with the CPU option to let the benchmark run on 1, 2, and 4 CPU cores. The results are clear. Doubling the number of available CPU cores results in almost, but not quite, half the execution time. We do have some overhead here from managing and scheduling all those goroutines. But still, the increase in speed is remarkable, and worth the little effort we put into making the code concurrent. And that's it for today's QuickBit episode. See the channel for more episodes, or visit my blog at appliedgo.net or my Go courses site at appliedgo.com. Happy coding!